Hello, classification and regression trees are popularly known as the CART algorithm we'll be studying today. So CART decision trees, as the name indicates, can be used for both classification and regression. But in CART, the tree construction is usually constrained to binary trees. And another difference is that Gini Index is used as the attribute selection measure. Most of the material for this slide has been taken from this book mentioned here. So CART, we want to do binary splitting. So a question which may have more than two answers can be split into two questions at a time. So this is an example. Assignment deadline could be urgent, could be near, or could be none. So for this we can split it into, look at this. Is the deadline urgent? Yes, no, and then you get a leaf. So this is corresponding to this. And when you say it is not urgent, then you say whether it is near. If it is yes, then this is the leaf here, and otherwise this is the last one. So this is how you can convert any n-array tree to binary tree by multiple level splitting. The attribute selection measure, Gini Index, this has been discussed in another video. I've given the links here. Would also give them in the description box. So just for completeness, we'll again write down the formula here. So if Pi is the probability that a tuple belongs to class Ci in the whole tuple set D or in the partition D, then the Gini index is computed as summation over all classes product of Pi into 1 minus Pi, and can also be written in this manner. And actually this is the impurity. When we say Gini index or Gini impurity, which means we want to have each leaf node to have a high purity, so Gini impurity should be less. So the value aimed at as the attribute selection measure would be smaller values of Gini. So two videos I have mentioned here. There's another possibility here, which is of adding weight to misclassification. So what does this mean? That you are now accounting for the misclassification in the tree. So suppose an instance of class I has been misclassified as that of class J. Okay, so we will attach a weight lambda ij with this misclassification. Instance of class I classified as J has a weight attached to it as lambda ij. So we create a matrix where the ijth value of lambda, it represents the cost of misclassifying I as J. So for this the Gini impurity is modified in this manner. So you are taking the product of the probabilities multiplied by this lambda ij. We'll go through an example later on. However, I just mentioned the formula here. Now, we said CART. So there's this regression word in it. So the new thing about CART is its application in regression. So which means the outputs are continuous. In classification, your target output is discrete or categorical. Now the outputs are continuous, so regression models are required, but the impurity measures have to be different. Our Gini index or previously studied information gain or gain ratio are all for classification. So we come back to our well known and well applied sum of squares error. Okay, so we will take the consideration of sum of squares error. Now the output at a value is a value at each leaf. See, in classification we remember it is a label. Okay, that this is in your classification, but in regression it is a value, and this value is the mean average of all data points. Okay, so a leaf would have several data points and each having their own value. So the overall value would be the average. We'll shortly see an example in the next slide. So we are making this as our optimization function. So the lesser the sum squared error, the better is the splitting value or the splitting feature. Okay, so we want to choose the best attribute, and this choice is now based on the minimization of sum of squares error. Okay, we choose the split point for a given feature by choosing it to minimize the sum of squares error. So this is for our continuous features. For continuous features, we are choosing the split points. So again, minimizing SSE. And then the feature that has this split point with the best SSE is chosen as the splitting feature at that point. And then we continue. So now we take an example. We just 5 tuples. This is a continuous variable, continuous valued attribute. This is a discrete attribute, and your target is in 1000 rupees, rupees K. So rent is your target. Now we are just comparing two trees on the basis of the splitting value of area. Okay, so we see there are 5 values given here. So we take area less than equal to 1200, suppose as the first splitting. So if you take this as the splitting, so area less than equal to 1200, yes, this leaf contains D1, D2 and D4. That's given here. On the other side, we get the other two tuples, D3, D5. So now what is the rent value here? It is simply the average of 1 plus 0.75 plus 2.7 this side, and for this one it is the average of 3 and 3.2. We take another tree where we are splitting at area less than equal to 1000. So the left leaf gets 2 values because it is now less than 1000, so it's only these two, and the other leaf has, so similarly we get the rent values. Now we compute the sum squared error. So we have seen in this square brackets we have taken the left leaf and then the right leaf, and likewise here. So the squared of, just for simplicity of understanding, I have written squared of 0.48. How does this 0.48 come? 1, the difference of 1 and 1.48. Because these are the differences, absolute differences. Difference of 1 and 1.48 comes in here. Similarly, difference of 0.75 and 1.48 comes here, and difference of 2.7 and 1.48 comes here. So this is the left leaf. Then the right leaf is difference of 3 and 3.1 is 0.1. Difference of 3.2 and 3.1 is again 0.1. So this is the sum squared error of T1. Second values have also been computed for the T2. This is the left leaf with only 2 tuples, the right leaf, and we get the sum squared value here as 0.158. So this is, the T2 is giving us a lower SSE. So we would choose, among the two, we would choose this as our splitting value. So I hope this small example conveys to you how the regression part of the cart trees work. We'll go through more examples in future video. Thanks for watching. Thank you.